but still your presence is very valuable to our this expert lecture. We will keep the record that whoever has attended this. It's a 1.5 hours lecture. At the end of the lecture, you can let us together we see that how the industry is at today. Thank you, sir, for coming. Good morning, all of you.
Good morning.
And thank you to Devendra for giving such a nice, we can say, introduction and start up on this talk. Okay. So, as we all know about ASICs, ASICs is nothing but what? This session will keep two ways, okay, two directions. So what happened? It will be interesting as well as informative. Okay, we'll not call it in industry. We'll not call it as a seminar or something. We'll call it as a KSS. KSS means what? Knowledge sharing session. So always in industry, when we do this type of talk, okay, we'll call it as a KSS. Okay, we always sharing a knowledge, okay, with each other. You have, let's say, alpha knowledge, and if I add something delta in it, then it's, or you can say the purpose of this talk is completed. Okay, so we just want what? Addition of that delta. Okay, so after this talk, you have to tell whether I am able to add that little bit delta or not. Okay, that is the main purpose of this talk, right? So ASICs, which what? I think so every one of you aware about the full form of ASIC. What is that? Application specific integrated. Yeah, that's right. Okay. So as such, sir saying, I am alumni of this GEC only. Okay. If I say or if I give my introduction, so I have started the journey of this engineering like you in 2005. In 2005 to 2009, I have completed my BTech in electronics. Okay, from CKP okay, college. And then after, I just joined over here in AMTech in 2010. So from 2010 to 2012, I have just completed my masters from here only. And we can say the first page of this GEC. From 2010 only, the MTech was started over here, and that was started by Kiran Trivedi sir, Dr. Kiran Trivedi. Okay, now he is at Rajkot, I think so. But he had started that initiative over here, and that is basically wireless only. Okay, you all aware about that. And then after, I have just completed my PhD from DGGEC. Okay? And if I say about the journey in this particular knowledge or academia, so I have moved all around. That means I have started my BTech, and in BTech I have done a project which is based on you can say embedded systems. So basically at that time in 2008-2009 my project was TouchNet. So that TouchNet is nothing but what? At that time if you visualize, so me and my father was sharing a single phone, and that single phone was Sony Ericsson T320, and it is keypad phone. So at that time we don't have a touch screen phone available. Okay, so at that time we have started a project like we are just connecting touch screens with graphical LCD, and we'll try to print whatever we are drawing on the touch screen. And the main purpose of that TouchNet was that once we'll draw something, it will be transferred to another unit, similar unit, and that will be helpful in many industries. Let's say one of the example that some surgeon is doing some surgery, okay, and if we need some help from expert, so over there, that thing can be helpful. Okay, expanded version of that the photo or video will be transferred to that device, and the expert will suggest that you have to operate over here or something like that. Okay, so that was my first project. Then after, in masters, MTech, as you know that wireless domain. So I have done my dissertation on wireless sensor network, WSN, you know already, or you aware about it. So in WSN, I have just worked on MAC layer. So MAC layer is nothing but what? Medium access control layer. So we are just dealing with the medium, that in a medium, when this particular wireless sensors are communicating with each other, they are using what? The band which is 2.4 gigahertz, and that is your Wi-Fi band. Or all other technologies, let's say smartwatch or phone or something else, it will be communicate in that particular band only. Okay, so that band is, you can say, a congested band. So how to gain access in that particular band? That was my project. And in PhD also, I have just continued with that. Okay, and I have added some AI, or you can say ML in that. And by doing that AI ML, I can improve, or you can say that particular wireless sensor network can gain access to that particular different technology. Okay, and then after my master, I joined one of the institute, you know, Maliba. So in that I have just worked for the 10 years as an assistant professor. And your Tarun sir is my colleague for the 10 years. And then after, I just switched to particularly eInforchips. Okay, so from last 1 year, I am as a DFT engineer over there in the eInforchips. Okay, and some of the students from your side are also over there as an intern. In a final year, in final semester, we are having a program, that intensive program. Okay, so from our college, we'll discuss later on also. From our actually industry, we are just arranging the interviews. Actually, basically over here we are arranging in a SCAT college, and we call the student over there, and we'll have 3 rounds for selection, and then after we'll just select that person, and that can be work over there as a understanding, and then after if he as well as the company feel that we can collaborate, so we hire that person. That way we are hiring the students or interns. Okay, we will talk later on also about the same thing. Okay, but when we talk about ASICs, so in ASICs we are having basically 4 domains, or you can say 4 departments where we are working. Okay, that 4 domains are nothing but core design domain. Then after, the second domain is PD, physical design. The third domain is, you can say, DFT, and the last one is verification. We'll discuss all about that thing. Okay, but I am just defining the particular title of this talk. Okay, role of DFT in ASIC. Okay, so that department, you can say, or this particular technology or method is, you can say, the department is small, but it's very important. Okay, because the tagline is there, a taste methodology that can save millions of rupees. Okay, why? Because when you are designing any chip, okay, I'll show you the chip also. I have bring one of the chip. Inside that you can see the small one. I will share later. Okay, so that chip, when you are designing, without testing, we can't send even a single chip to the market. Okay, each and every chip, whatever design, that will be tested. Okay, and then after only it will be sent to the market. Okay, in testing or in verification, or you can say in QC, quality testing, we all know that, or we all have that understanding that some of the samples are only tested. Okay, when you go in any manufacturing unit, rather than this ASIC, okay, or in chip, you can say that 1,000 of products are manufactured. So out of that, 10 samples are there, random. and then after that 10 samples are tasted, and if that particular samples are okay, then the whole lot, 1000 lot will be granted as a quality check. Okay, but over here it is not possible. You have to taste each and every chip. Okay, why? We'll see in this particular presentation. Okay, one by one when we go to the presentation, you will understand. Right? So now we will get the understanding of that particular little bit understanding of DFT. Okay, and that will create interest in you. Okay, why you have to attend it. Okay, so today's agenda is we'll just discuss, or you have to tell me the current development in semiconductor industry. Can anyone tell me what is going on currently? If you are aware about the news, you already know the different things that's going on.
Qualcomm and MediaTek. Qualcomm and MediaTek.
Qualcomm and MediaTek. Yeah. Then
4 nanometer chips, SoCs for mobile and mobile devices.
in development.
In development.
Okay.
4 nanometer.
4 nanometer.
Currently we have Snapdragon 888 Gen 2.
Yeah.
Which is working on 4 nanometer design, fabrication design.
Okay. So
And
what is 4 nanometer?
4 nanometer is feature size of transistors on chip, as we learned in VLSI.
Yeah, that's right. Feature size. That means if in layman language. It's a channel length.
Yeah, channel.
It's a channel length. Okay. Anything else? So that is one of the things that 4 nanometer technology is available in the market. Okay. And currently research is going on 3 nanometers and 1.5 nanometers also. Okay. And above that also we are trying to do that. Okay. By quantum technology. Okay. Then in prospect of industries, Micron technology is there, who is investing over here in Gujarat. Okay, another Vedanta is there. Okay, then recently our honorable PM has done one of the things, the biggest conference, Semicon. Okay, so over there with all big cool companies gathered and discussed, and they have discussed about the ecosystem. Ecosystem is nothing but what? When you want to develop any industry, you require some specification is required over there. Okay, so they provide that specification to one of the industry. But for one of the industry, when they are developing all the things, let's say if we talk about helipad or something, that is a single thing. But let's say air quality and other different things are there. So if they develop for one of the industries, whatever, that can be applicable to all of them. So you know the Dolera, over there they are trying to develop that fabrication laboratories in which we will develop our ICs. Okay. One of the fabrication lab is also there in India. Do you know that? Which one? In Chandigarh. SCL Chandigarh laboratory is basically developing the ICs, but that is not for commercial use. They are developing for defense. They are developing for defense. And whatever we are going to implement over here in Dolera, they will develop what? For commercial use also. Okay. So that you can say current development or recent development in semiconductor industry. Okay. So semiconductor industry ecosystem. So these are the basic parts you can say that will be all around in semiconductor industries. Okay. Samsung, Apple, Cisco, Intel, Texas Instruments. These are the electronics system level development companies. Okay, so that companies develop what? A whole product. Okay, but to develop that whole product, what they require? Okay, so they require different IPs, they require different circuitries, different designs. Okay, so that designs or IPs will be developed by whom? Research institutes, okay, and academics. So they will do what? Research on the different domains, and they will provide what? Different kinds of IPs. As well as IP vendors are there. So IP vendors will do what? They also do the research, and they will just gain some of the IPs. Like recently, you can say RISC-V architecture. Okay, RISC-V. RISC-V means RISC-V architecture. So that is actually freely available to all. Okay, if you want to the code for that, you can also get the code from internet, and you can work on that at your distance. Okay, if you want to add something in that, if you want to improve the performance of that particular RISC-V architecture or anything. Okay, so that type of IPs are there, and that IPs will be used inside your circuits directly, inside your circuits directly. Let's say suppose we'll have when we talk about SOC. So SOC means what? System on chip means we'll have everything on a single chip. Everything that means what? Everything. Processor,
control unit,
memories, input outputs, control units, each and everything will be available on single chip, right? So when you talk about memories, so memories will be in how much size? It's in GBs, or sometimes it's in TBs also. Okay, so for testing of that memories, you require what? Some kind of hardware. So that hardware is also built inside the SoC only, and that's called MBIST. We'll discuss later on. That is also covered in this DFT, because testing all around is nothing but what? DFT. Okay, testing all around is nothing but what? DFT. So that MBIST is nothing but, you can say, a IP. Okay, intellectual property of Mentor Graphics, which is now we can say Siemens. Okay, so they have developed one of the IP, and that IP can be directly used to test the memory. Okay, and that will be inside your chip only. Okay, so MBIST, full form of MBIST is nothing but what? Memory built-in self-test. So it is inside the SoC only. Okay, it is something like in our mobile also, or in our any electronics device, if you can say, over there one self-testing mechanism is there. Okay, sometimes you write some code or 3 switches when you press, so it will go into the debug mode. Okay, and in that debug mode, you can test each and everything of your mobile. If we talk about automatic washing machine, over there also that self-test is there. So similar kind of self-test is there inside the SoC. Okay, for memory. Okay, for remaining logic, we are inserting design, or you can say DFT. Basically, it's called scan insertion. We'll see also. Okay, 6 different technologies are there. Okay, so that is about IPs. Then foundries are nothing but what?
manufacturers.
For production of that particular ICs. Okay, whatever the final design is there, that design will provide to that particular foundry, and foundry will do what?
Manufacturing.
They just manufacture that particular design on a silicon wafer, and then after we will get a kind of this. Okay, this is one process actually. Whatever we are using in our laptop or in our desktop, it's a 3 centimeter by 3 centimeter size, but actual size will be something like this, and that will be extracted. Why? Because in this you can't able to connect. Okay, so that's why we are extracting the connections of that particular processor. Okay, and we are making that particular processor as a big size. Okay, and that is called packaging. And whatever the micron technology over here, that particular company is coming, that is basically for packaging purpose. So whatever the developed chip is there, how we can convert into the package. Different kinds of package are there. DIP package, QIP package, the different kinds of packages are there. So in that they will be converted or they will be developed. Right? So that foundries are there, that design services. So like our companies, they will provide what? Design services. So design services means, let's say some of the customer is having some specific requirement. So we'll just get the requirement from them, specification from them, and we'll provide the design for them. Okay, from design to tap out. Okay, so that tap out is nothing but what? A final design, you can see. So the final design, in between some stages are there. So we'll discuss that later on in this slide. Okay, which are the different stages. Okay, we'll get only the specification from the customer. Let's say in one of the chip in which I am working, it's a networking chip. Okay, so they just develop a networking chip which will use this Wi-Fi connection. Okay, so for that they just provide a specification. Then our designer team will design based on that particular specification, and they develop what? A code. And that code is nothing but what? A working of IC. Then after, our PD team will convert it into what? The code is written in which language? આપણે VLSI માં કઈ language? Verilog and VHDL. Okay, so that code will be written in Verilog and VHDL. Okay, or you can say RTL. Okay, so that RTL will be converted into what? Gate level netlist. Gate level netlist. That means whatever the description you have written, that will be converted into the gates. Converted into the gates, and then after our part will be done. Okay, and that part is nothing but DFT. Okay, so then after we'll add some fixes which will test all the circuitries. Okay, I'll tell you why we require to add that fixes. Okay, otherwise it's not possible to test that particular IC. Okay, I'll tell you and I will explain you why we require to add that. Okay, otherwise your one processor will take let's say hundreds of years to test. Only one single processor. Then you will get your processor after your 3 to 4 tests. Okay, so it's not possible. Okay, so that's why we are adding some fixes. So this DFT not only save your rupees as well as it will save your time. It will save your time. Okay, so that DFT. Then CDA and Cadence company, CAD company will do what? That Cadence, Synopsys and other company, Mentor Graphics will do what? It will provide EDA tools. Okay, it will provide EDA tools, Electronics Design Automation tools. Okay, so in that tools only we are working. Okay, I'll give you the list of tools also at the end, that which tools we are working. Okay, but it's not freely available, it's licensed. So you require license for that, and its license are very costly. But for that also, one of the organization is there. Okay, which will provide you the license free of use for institute purposes. So I will share that information to Tarun sir, and you can contact them. Okay, so I'll say to sir also, if they apply, for whole institute they will get license for it. Okay, DC tool as well as VCS tool is there for simulation. Different kinds of tools are there. Descent tool is there. So they are providing that. Okay, so you can get it. So this is all about ecosystem. Little bit about my company. You can say eInforchips. It's acquired actually by Aero Electronics. So we'll have, let's say, more than 3800 employees. Okay, and we have 12 design centers. Okay, as well as many you can say service centers or sales centers all around the world. Okay. We are not only working in you can say ASIC, but the different domains are there. So PES is there. Okay, product engineering services, which will working on different domains. Okay, obviously ASICs will work in semiconductor industries. Okay, so this one is you can say the organization chart. Okay, so we'll have ASIC. In ASIC we'll have 4 domains as I told you. Okay, design, co-design, verification, DFT and physical design. And we'll have PES. Too many students from this GEC only in my page or in my previous page, BTECs, are there in PES also. Okay. So yeah, this is our esteemed customers. We are working with this all companies. Okay, they just provide us different projects and we work on that particular project. Okay, some of the well-known companies I have mentioned over here. Okay, and some of the companies that I have not mentioned. Okay, but one of the company I can say GUC, Global Unity Corporation. Okay, so that company is, you can say, child company of TSMC. Okay, and TSMC is nothing but what? It's a foundry. It's developing a different ICs. Okay, different ICs. So in one of the projects over there only I have worked. So this is all about our company. We will start with the VLSI. So you already know about this thing, right? Currently, whatever the size of wafer is there, that is 10 to 15 centimeter. Okay, and they are just making it bigger. So when you make a size of a particular wafer bigger, what happens? Wafer is nothing but what? This piece. Right? It's a silicon disc. When you increase the size of wafer, then what happens? Yeah, number of dies. And what we call it? Dies for one process. So this one is a part of one wafer. This one is a part of one wafer, right? So when you increase diameter, what happens? You can increase the number of dies. Okay. Sometimes some people have a question over here. Okay. I don't know you have that question in your mind or not. Why this wafer is circular? Why not square? Because whatever die we are cutting from it is what? Always square. So why this wafer is circular? Why it's not square? If it is square, then what happens? You can utilize whole wafer. Okay, each and every part. Over here, when you are making it circular, then what happens? Some of the part will be not used. will be not used. Surround part, okay, will be not used. Okay, because you can see over here half dies are there. Okay, but that half dies are not manufactured. That part will be left as it is. Left as it is. Okay, why? Okay, then you have to see. Then after, as I told you, the die is nothing but a rectangular piece, or you can say your processor, actual processor. Okay. On that we are adding layers. On that we are adding layers, because you all know, if you want to design a transistor, what you have to do? How the transistor will design? From actually which metal or material that particular transistor was designed? Silicon or germanium, but actually we are using silicon. Okay, everyone. So from silicon, what we are doing in that, direct silicon can be used as a transistor.
No.
Then
Doping and
we require
impurities.
to add impurities. Okay, and different kinds of impurities when we are adding
N-type, P-type.
N-type and P-type impurities. So when we are going to add that N-type or P-type impurities, it will create what? N-type and P-type semiconductor. And by joining that, we are creating what?
FETs.
Junction. And when two junctions are there, we call it as a BJT. Okay, or transistor. Okay, so we are not joining it, but what we are doing?
Creating
We are adding impurities in such a way that it will create a junction. It will create a junction. So different masking layers are used, and from that masking layers we are using, or we are adding impurities in it. Okay, and we are making what? Transistor. Okay, so let's say 12 to 15 layers are there on that wafer. Okay, out of that 6 to 7 layers are used to create transistors, and remaining 6 to 7 layers are for what? For interconnection. So basically, processor, what is that? If we go inside the processor, what is that?
transistors and interconnections.
Directly transistors. When you go inside processor, what is that? First of all, you will get a block. ALU and CU. Okay. ALU and CU. Then in ALU, what is that? Again a different small blocks.
Combinational blocks.
Combinational and sequential blocks. Okay, both are there. Okay, combinational and sequential blocks. Half adder, full adder. Okay,
Mux
parallel, or you can say registers, shift registers, and all the things are there. Okay, and that is made up of what? Gates. And ultimately, gates are made up of transistors. Okay, so from transistor, if you see the bigger picture over there, you will get what? Processor. So to make that processor, you have to do what? You have to make a different connections. Okay, from transistor to gate, gate to combinational circuit, sequential circuit, from that ALU, and then you will get what? A bigger picture of processor. So that 6 to 7 layers are used for that. Okay, for interconnection. Okay, if you want to make a NOT gate, how many transistors you require for NOT gate? Two. For NOT gate. It's your DLE, first chapter or first topic. Only one.
PMOS and NMOS.
Okay, PMOS and NMOS. So one is pull-up network or pull-up logic. Okay, and one is pull-down. Right. Okay. Then Okay, so we'll just see how that particular processor was designed. Okay, so first we'll just melt that particular silicon and we are making what? Wafer from it, and then after we'll add in some impurities as well as silicon dioxide layers, and we are making what? A full wafer. Okay. In that we'll just check the thickness as well as its crystal layer and resistance of that particular die, that whether it is useful or not. Okay, and then after we'll make it what? By adding impurities, masking layers or different layers, we'll make a IC. And then after, see, this type of extra things will be there. Okay, these are nothing but dies and this extra part is there. Okay, that can be removed. Okay, then we'll cut it and we'll package it. And then after, this machine is nothing but what? Actually, this machine is used before cutting. This whole wafer will be put on this machine. Okay, and that machine is ATE, automatic test equipment. Automatic test equipment, and that test equipment is used to test each and every process. So now the question is there, how the connection will happen. So over there, a small probe is there, and that probe having a smaller connection. You can say the size of that particular connection is less than your hair thickness. That will be connected on each and every die, and it will be tested. Okay, and when each and every die is tested, they will perform a marking. That marking is nothing but what? Some of the dies are not used or faulty, so that will be marked as a black. Okay, so once that die will be marked as black, after cutting it will be thrown into the dustbin. We can't use it. Okay, and whatever the good die, that will be go inside the package. That will be go inside the packaging. Whatever die I am having, that is marked as a bad die. I will show you. Back side, black mark is there. Okay, so this one is your bad jacket, not working. Then only we are using. Okay, otherwise this one piece is of 20,000. Your processor price. Okay, so something this type of arrangement you can see that out of this first die, this green is nothing but successfully tested. Some of the colors and partially tested and fully tested, or you can say failed dies are. So this chart is created, and then after we'll cut each and every die and we'll use it. Okay. Partially tested dies are also used. Why? Because it's failed to some conditions only. Let's say some of the dies will fail your delay related test. I will show you later on which kind of tests are there. Delay related test, that means what? It will not match whatever for the frequency you have designed. Our processor. Okay. Whenever you purchase a phone or any processor, what you will see? First,
Clock frequency.
clock frequency. Wow, very good. You are very intelligent. Nowadays we are using, we are just checking what? How many cameras?
2.4
How much
gigahertz.
the particular pixel size or something, your resolution is there. Okay, but it is not the thing. You have to check what?
Clock
Frequency. Okay, because based on frequency, your speed will be decided. Your speed will be decided. So some of the dies will fail in that particular frequency matching, but that can be used for some other purpose. That's why we are not throwing that dies to the garbage. Okay, we are using for other purpose, not for a critical purpose, right? Let's say suppose in some of the medical equipment, if we are using that particular die, then what happens? Due to delay.
Someone will delay.
Okay, finish. that person. If we are using that knife for testing the heartbeat, and that particular chip will be delayed, and the straight line will be before it's displayed. Nothing is done, right? So that's why we are not using over there. So for critical application, we are used successfully. Okay, and for some other application, we are using this partially tested done. Okay, or partially powered. Okay, this one is your actually design flow. Okay, how that particular SOC or ASIC will be designed. So first of all thing is nothing but we are getting the specification from customer. Specification is nothing but what?
Required input and output.
Yeah, required input output, the frequency on which that particular IC or circuit will be worked, then the particular task of that, each and everything will get as a specification. And in that same, we are getting what? DFT specification also. Okay, and chip microarchitecture. Because whenever we are going to design a new chip, we are not always starting with the zero. We are not always starting with the zero. I will show you later on also. Because whenever we design a chip, in that chip, 20 to 30% part will be from the before baked chip. Okay, directly we are using the same architecture or same block from the before created chips. Okay, 10 to 20% part only we are adding extra in there, and remaining part will be your memory. Remaining part will be your memory. Okay, so that way we are performing a design. Okay, so first is specification, then we'll create RTL code, okay, and we'll do the verification. Which kind of verification over here? કોડ તો આપણે જ બનાવ્યો છે, પછી એમાં શું વેરિફિકેશન? Whether it means or it meets to our specification or our requirement. Okay, only the code. So that code will be tested. Okay, and it's called, you can say, logic check. Logic check. Okay, LEC. Sometimes it's called logic equivalency check. But that logic equivalency check will perform at each and every stage in ASIC design. Okay, let's say when you add something in your design, or if you remove something from your design, at each and every time we'll perform what? LEC, logic equivalency check. That whether your functionality will intake or not. Okay, then after synthesize. Synthesize means what? As I told you, from RTL to netlist. From RTL to netlist, gate level netlist. Okay, we are converting it. Then next our DFT will come. So in DFT we will do JTAG insertion. Okay, this JTAG is nothing but joint action task group, but that group, it's something like IEEE group. They are creating what? Different kind of standards. The same way, this group is also creating what? One standard, and that standard is used for what? That is IEEE 1149. Okay, and that standard is used for accessing your chip. So they are creating one pod, and that pod is nothing but TAP. It's called TAP. TAP. Taste Access Pod. So from that only we are accessing our chip. We are accessing our chip. Clear? So that will be inserted. Then MBIST will be inserted. Scale change. So that is the part of your DFT. Then TPR. This is nothing but taste point insertion. Okay, and LEC is nothing but logic equivalency check. So that all the things will be done. So this one is nothing but your JTAG. Okay, you can see it's not very clear, but this one is your case access code, and it will access all your things, Okay, then after the kind of embed. Okay, this one is your memory, and that memory will be pasted, and that particular hardware is inside your chip. Okay, that's why it's called built-in surface. And we are writing scan insertion. So the scan insertion is nothing but what? In your design, you will have combinational as well as sequential. Now, in sequential, we'll study how many flip-flops? Flip-flop का
SR JKD 5
कितना? 5. SR JK DE DND 4 master slave. Any age trigger? Mel? Anything else? Level trigger?
as a layer.
Only 4 types of
4 types.
level trigger and age trigger is another thing. And master slave is a remedy of your race around condition. Do you know that JK flip-flop will have kind of race around condition when you provide 1 as an input. Okay, so it will toggle its output, and that's called a race around condition. So to avoid that, we'll do what?
Master slave.
We'll create a master slave design or age trigger, or we'll just reduce the size of clock. Okay, so that is other thing. But 4 flip-flops are there.
JK.
But out of that 4 flip-flop, in industry or in design, we can say most of the time we'll use 99% time we'll use D flip-flop. We'll use D flip-flop. Remember that. Okay, remember that. 99% time we'll use what? D flip-flop. So each and every design, whenever we'll go and see, we will find out what? D flip-flop over there. And you can say the number of D flip-flop in your design will be it's in a million. It's in a million. Okay. In one single design, one processor will have million of D flip-flop. Okay. And your combinational logic. Combinational logic, that means what? Gates. Your different gates. And combine of that two, you are making your design. Clear? So in design, you will have D flip-flop. You will have D flip-flop. And your combinational logic. Okay, so the scan insertion is nothing but what? We are just converting D flip-flop into the scan flop. So you take a D flip-flop, and we'll have something extra. What is that? We'll see later on. It's a mux. But why we are adding? We'll see later. Okay, so this is DFT, then physical design part. So physical design part will contain what? PNR, placement and routing. Different blocks we are using. Okay, as I told you in SOC or in ASICs also, we are using a different things, memories, processors, different kinds of logic. So that you can say a block, different blocks. It's called in an industry language. It's called macro. A small macros are there. So that macro placing in your design or in your die, and then after interconnection of that. So that's called a routing. So placement and routing will be performed by PD people. Okay, PD people means physical design people. Okay, as well as they will perform CTS, clock, tree, synthesize. That means what? Each and every macro, you can say D flip-flop require what? Clock. So how that clock will be propagated in your design? Let's say from one end to other end. D flip-flops are there, and if you connect them, the interconnection wire is used, and due to that, what happens? Your delay will arise. That should be not there. So that taken care will be done over here in CTS, clock tree synthesis. Each and every clock will get clock at the same time. Sometimes in your design you will have multiple clock hours. It's possible. Okay, so that will be generated through OCC kind of structure is there. OCC is nothing but what? On-chip clock. On-chip clock, and in that basically you have already studied PLL, phase loop lock, phase loop lock. So that circuitry will be used, and that circuitry is as well as divider. So that will make what? A different frequencies or clock from chip only. So we are providing only one clock, and that will be divided into the different clock. Okay. Then after this PNR, again DFT part will come. So this DFT part is nothing but what? You can say test vector generation. Let's say I'll give you one AND gate. Okay. So how you can test it? AND gate to know everyone.
Yes.
Let's say I am giving you one AND gate. And it's your AND gate. I forgot actually. Sometimes I draw another gate and I say that this one is AND gate. Actually AND gate?
Yes.
Okay. So how you will test it? If I give you the AND gate, how you will test it? How many inputs are there? Two inputs. Two inputs. Two inputs. And output?
C.
One. Okay. So how you will test that whether the AND gate is working or not? Truth table.
Yes, sir. Yes, sir. A, B, 0, 0, 0, 1, 1, 0,
Okay. So that means to test your AND gate, you require what?
Test vectors.
Four test vectors. Okay, right? To test your AND gate, you require what? Four test vectors in a simple language. Okay, that means at the input side, you are providing the input and you are checking whether output is coming or not. The same thing we are doing over here. This one is nothing but what? Your test vector. We are providing as the input and we are checking whether the output is coming or not. It is not exactly like this. All that means what? Each and every inputs and outputs are included. But over there we are having PI. PI is nothing but primary input. Then we are having PPI. PPI is nothing but what? Pseudo primary inputs. I'll tell you. And then after we'll having PO, primary output, and PPO, pseudo primary output. And comparing that PO and PPO will tell that whether your chip is working properly or not. Okay, but that test vectors are nothing but similar to this truth table. We are giving input and we are checking output. Whether it is coming or not. And that process is known as ATPG. That process is known as ATPG, automatic taste pattern generation. Automatic taste pattern generation. Okay. As well as we are generating taste vector for MBIST, as well as we are generating taste vector for LBIST. LBIST is nothing but what? Logic BIST. Sometimes in some circuitries you require that you have to include testing circuitry inside the chip only. Inside the chip only. So that type of technology is known as LBIST, logic BIST. Okay. And then after JTAG and IP. For IP, again we require testing patterns. Why? Because IP is nothing but what? It's a proprietary of someone other vendors. Okay. So they will not give you all the details of that IP. They just give you the block. Okay. Or a code, or you can say your their design in other coded form. Okay. In other coded form that can't be decoded. So at that time you can't test that IP. So that's why they provide you what? The vectors. So that test vectors are used over here for IP testing. For IP testing. Clear? Clear? So sometimes we are using that IPs also. Okay. Then tap out means final design. Okay. Once each and every thing will be completed, or you can get it's a fine. It will be the tap out. So that means your design will be provided to the manufacturer.
Foundries.
Okay. Or foundry, you can say. Okay. And then foundries will do what? Wafer manufacturing. And then after silicon bringer. Silicon bringer is nothing but what? As we have discussed earlier. Okay. The making of die, and then after testing of that die. Testing of that die. That's called silicon bringer. They will just develop 100 or 200 chips only first. And then after they will test each and every chip. Okay. If they found that out of 100 chips, 99% of chip or 99 chip is passed, then what happens? They just go for production. If not passed, let's say 50% is failed, then what happens? They just find the reason why it's failing. Some DFT is problematic or malfunctioning, or some design is malfunctioning. So again they will do what? The similar kind of process. And then after, again they will come to bring up. Once the bring up is done, then after they will go for products. Then after they will go for products. So that after production, again each and every IC, or you can say die, will be tested. Each and every die will be tested. Okay, clear? So this is again the same flow, but I have just written some sub parts also. Okay, sub parts also. Whatever the red colors, that red color is nothing but your front end design. Front end and back end, two things are there. Front end design and back end design, two things are there. One is logical related and one is physical related. One is physical related. And DFT will fortunately come at both sides. Come at the both sides. Okay. In front end, you have to add some design that will use for testing, and in back end, what you have to do? You have to generate
IP.
Taste. You have to generate taste. ADB. So that taste will use for testing that IC. Vectors. That vectors will use to test that IC. Okay. Moore's law. Everyone aware about that? हाँ, हमारा जो एक्सपायर नहीं है, थोड़ा टाइम पहले खबर है न्यूज़ में आ रही. So what is that Moore's law?
Number of transistors in every hour.
Don't have every
every 1.5 years number of
1.5 years, or you can say 18 months.
18
The size of
number of transistors on the
transistors will be
doubled.
the number of transistor will be double, or the size of transistor will be reduced by half. Reduced by half. Clear? Reduced by half. So always you can say your feature size is decreasing. Okay. So what happens when your feature size is decreasing? Let's think about that 5 nanometer technology. So your transistor size or your interconnection size is near about that 5 nanometer. So you have to design a system which will do what? Which will create this 5 nanometer of gate, or you can say 5 nanometer of transistor, or 5 nanometer of interconnecting wires, and between that two wires again you are having a space of 5 nanometer or less than 5 nanometer. So there are possibilities that interconnection can be there, or there are the possibilities that one wire is not connected to the another wire, which it means. Okay, so that's called a open. Okay, so that kind of fault may arise in your design when you are manufacturing the IC. You can say this black one is nothing but what? Interconnection, but it is not connected due to this hole. Okay, so that hole will create what? Open defect. Okay, and sometimes it may be possible due to impurities. Due to impurities, your two interconnecting wires will be connected. So that's called short defect. That's called short defect. Okay. So open kind of defect, short kind of defect is there in your IC. And for that only we require what? Testing. So testing is a little what? CUT, that is circuit under test. Whatever the processor we are having, that processor will be in the test, and we are providing what? Input. And we are checking what? Output, whether it is same or not. If it is same, you can say your IC will be passed. If it is not, you can say your IC will be failed. Right? Importance of testing, you can read again. It provides that your product will be fault free. Okay, then you can test your device at different stages. Okay, clear? Let's say suppose IC manufacturing is there. At that time you can test your IC. Then after that IC can be fitted on some board, something like your motherboard. Let's say suppose on your motherboard you are fixing your processor. Okay, other types of processor, that means a graphic processor, can be soldered on that particular motherboard, right? Or other chips are also there. Let's say your particular Wi-Fi access related chip, NIC we'll call it. Okay, network interface card, that is soldered on your motherboard. Okay, so that is another stage, you can say. Okay, from your chip you are coming to what? Motherboard, and there also you can perform what? Testing. From motherboard, now that motherboard is installed in your laptop. So that is another stage, that your device is ready and you are testing over there. So over here, rule of 10 will be applicable. Rule of 10, that means what? If you check your defect at lower level, your cost will be lesser. That means if you check your IC only, it will cost you something that $10. If your IC is faulty, let's say it's a $10, so you can change it. But if you without testing, if you put that particular IC on motherboard, then now your motherboard is of $100 or $1,000. And if it's not working, then your $1,000 was wasted. Let's say you are not checking over there also, and you are going to what? Laptop. You have installed that faulty board. It is due to only that IC. But you are installing that faulty board on what? Laptop. And you are testing the laptop. Now laptop is of 20,000 or something else. What happens? Your that much rupees what? waste. Okay, so it's good that you are test your device in a early stage. Okay, clear? Device failed due to what? Insufficient dropping or process errors. Some kind of errors are there. Okay, and two photographs I have already shown to you. Okay. We already discussed about this thing. Okay. DFT when we do this ADPG, MBC insertion, scale, JTAG insertion. Okay. And over here in backend we will perform what? ADPG and pattern validation. Pattern validation, that means what? We are just checking whether this pattern is working or not. Whether this pattern is working or not. Okay. So these are the different domains of DFT. These are the different domains of DFT. You can work on any one also, or sometimes project, based on project, you can work on each and everything. Okay. In my project, whatever I am having, as I told you, the networking chip from GUC, I am working with MBIS. The first step. Your first step is MBIS. When you will get your design, always the first step was you have to insert MBIS. Okay, why? Can anyone tell me? Why we have to do first MBIS? Because in your SoC or in your chip, always memory is there. Okay, and you can't test memory. You can't test memory by ordinary way. Because memory is a different kind of thing. It's having what? It's having a register. Okay, for story. So what you have to do? You have to write on the memory, and then after you have to read that memory. So that test is nothing but, you can say, retention test. Retention test, that means what? First we'll write each and every location of memory, and then after we'll read that each and every location. So what happens? Through that test we can able to find out that whether that particular cell or whether that particular register able to retain its data or not. So that's called a retention test. Okay. So that is somewhat different kind of test. So that's why we are first inserting what? MBIS. Okay, in our logic. So when design will come, we'll first do what? We'll insert the MBIS inside your design. Then after, second step will be you have to insert JTAG. JTAG means test access code, from where you are accessing your test. Why it's required? આપણે જ્યારે બી આપણે IC કે પ્રોસેસર પરચેસ કરી, when we are going to purchase a processor, what we are doing?
મધરબોર્ડ પર એ સોકેટ છે કે નહીં,
fix it on a motherboard. Okay, and each and every pins on it is useful for some kind of input and some kind of output. Let's say just telling you that out of that, let's say 100 pins are there. Out of that 100 pin, I require 50 pin for testing. And after that, testing is completed. It will be no use then. So you will have only 50 input output. So that is loss of input output pins. So that's why this test access port will be inserted. Okay, and that will use only 1 or 2 pins. Basically 4 pins are there, but out of 4 pins, one is your reset pin, one is your clock pin, one is your input pin, and one is your output pin. Remaining all the pins here are your functional pins. Okay, so to save that pin area, because always we are having what? We are hurrying in reducing the size. When we are designing processor, always we are thinking of what? Reducing the size. Why? Because you want that whole computer will be inside your watch. So 3 by 3 centimeter can't fit in this. So we are reducing the size. And when we are reducing size, what happens? Again we have to reduce the pin count also. Number of pin count also. So that will be there. Clear? That will be there. So JTAG, then scale insertion, ADPG. Simulation is nothing but what? We are checking this pattern. We are checking this pattern by simulation, providing vectors and checking whether the output is coming or not. And LEC is nothing but logic equivalency check. In whole process, we are adding too many things inside your design. So by adding that things are nothing but what? Mux or gates or something else. By adding that things, whether your functionality is changed or not, that we have to check. બરાબર? આપણે વોશિંગ મશીનની સર્કિટરી બનાવતા હોય અને એમાં ટેસ્ટના બધા પર્ટિક્યુલર ફિક્સીસ એડ કર્યા અને એસી માટે બની જાય તો ઇટ્સ નોટ ગુડ ના. That's why we have to perform what? Checks. That whether your functionality is intact or not. Clear? Then after we'll go a little bit faster. There is nothing but different types of defects. Defects are nothing but what? Impurities that cause open, impurities that cause short. Sometimes this kind of things will be there, open, short will be there, okay? And sometimes this crack, small crack is there. That will do what? That will add resistance. That will increase resistance. Okay, so that type of fault is also possible. And due to that resistance, what happens? Your transistor can respond slowly. The transistor can respond slowly. And once your transistor will respond slowly, what happens? Your frequency or your functional frequency will not match. Okay, so that is again another kind of fault. Okay, now why we require this DFT? So that is this. That RISC-V architecture, as I told you, it's having you can say 136 of PI, primary input, and 268 of primary output. અહીંયા આપણે AND gate ને ટેસ્ટ કરવું, so we have provided what? Four combinations or test patterns. Let's say I have taken one example. Let's say you have 129 pins of input. Then how many combinations are there? 2 to 129. You can't even read it. That much of patterns you require to test that circuitry. Okay, and if you use your AT is nothing but what? Automatic testing equipment or test equipment. If you use 1 gigahertz of speed, 1 gigahertz, that means what? 1 gigahertz. 10 raised to 9. Okay, so at that much speed, if you provide your test stimulus, then also it will take how much of time?
2.1
to test your one IC. Or you can say to provide this much of pattern. Okay, and for that only we require what? DFT. So when we insert DFT, your things will be reduced. Okay, and you can, how it's possible, how it's sliced into 64 and how this fault will be reduced, I will tell you later on. But it will be reduced to what? This much time. Your one processor can be tested in 0.1 nanoseconds. Okay, and it will reduce what? Your testing time as well as your cost. Testing time as well as your cost. Okay, now actually when that different kinds of faults are there, okay, that fault will be converted into models. Okay, always in engineering we'll do what? We're converting our things, physical things into models, and we'll work on that model only. Okay, so over here, four kind of models are given. One is stuck-at fault. Stuck-at fault means what? Your particular pin will be stuck to any value. Means from here, let's say VCC is going on, and that particular wire is short with what? VCC. So that is what? Stuck-at one. Always you are getting what? At that particular pin, you are getting 1. So that's called a stuck-at 1. Stuck-at 0, that means what? Either disconnection is there or it's short with ground. It's short with ground. So always you will get what? 0. So that's called stuck-at fault. Okay. Another one is transition delay fault. So transition delay fault is nothing but what? As I told you, that hairline crack is there. Due to that, resistance is increased. So what happens? Delay. Delay will be there in the response of transistor. And that delay will introduce what? Transition delay. Transition delay is, that means what? It's kind of propagation delay. It's a kind of propagation delay. You are providing input, and after how much time you are getting output. Okay. So that's called a transition delay. Always each and every device will have some of the propagation delay, but that should be some limit. If it is in limit, if you are providing input, let's say OR gate is there, and you are providing, or AND gate is there, and you are providing initially 1 0, so your output will be 0. And if you change this A to 0 to 1, so 1 1, that means what? Your output should be what? 1. So after some delay you will get what? Your output will be 1. But due to that crack, your resistance is increased. So what happens? You will get your response after some time. After some time. So that's called a transition delay fault. Clear? Another one is your path delay. Path delay is nothing but what? Whole path we are considering. Over here I am talking about what? Only one AND gate. Now we are talking about what? Whole path. In between a different combinational logic is there. And from that path to path we are discussing. So that's a path delay. And this coupling is nothing but what? Effect of other. Effect of other. Let's say in memory, one cell is there, and its neighbor cell is there. In one cell, we are adding what? 0 value. And when we are writing in its neighbor cell 1, automatically that cell also get what? 1. So that's called a coupling. Due to neighbor cell, your value is changed. So this kind of faults are there. Okay. Now how we will detect it? So we'll use a scan cell. Scan cell is nothing but what? Again, a D flip-flops are there. And in D flip-flop, we are adding what? 1 mux. Different kinds of scan cells are there. But basically in industry, always we are using what? Mux D scan cell. That is what? We are adding 1 mux before your D flip-flop. Okay, before your D flip-flop. This is your ASIC. ASIC means what? ASIC means scan enable. One is your DI pin. DI pin is your D flip-flop input. One is your SI pin. SI is nothing but scan input. Why we are using? We'll see later on. Scan input. Clock is there and output is. Okay. So why we are using? So it's something like this. Architecture. Okay. As I told you, in your design, you will have what? Combinational as well as sequential. This is part of design only. Okay. This is part of design only. Let's say suppose this is not there. Something. This SI and SE is not there. Then your simple D flip-flop is there. And it's taking input from somewhere and it's giving output to your combinational circuit. This type of circuit is there. Now what we will do? We will just insert mux over here. So it will be converted in this. And we are stitching each and every mux. Through SI. So it's a chain. You can see it's a chain. In our industry, we'll call it as a scale chain. We'll call it as a scale chain. Now what happens? See, in your combinational circuit, you'll have X number of inputs over here. X number of inputs. We have added extra input for your circuitry. From where? From here. How it's possible? We'll give input from this one pin and we'll perform shifting. So what happens? We can set each and every each and every gate flip-flop, and thereafter we'll provide its output to our combinational circuit. Okay, so you are getting more inputs, so you can get what? More controllability of your circuit. Okay, and at the same time you are having let's say Y number of output, but you are getting what? Extra output by connecting this to the connecting it is already connected by observing from here. So you can increase your observability. You can increase your observability of design. So this way we are inserting the scale inside. Okay. How it will work? I'll show you. Let's say suppose this is a very simple design. How we design after manufacture the design. We'll have let's say D flip-flop in millions and we are designing. Okay. Each chain. Chain में कितना flip-flop है? Only three. Each chain have more than 500 flip-flop and 30 to 40 chains are there. That type of design is there. Okay, and we are controlling only through one input. And how? We'll see. Okay, so this one is your simple design. So when you insert that scale, so it looks like this. Initially simple RD flip-flop is connected. This part is not there. Okay, this part is not there. We have inserted. Okay, we have inserted. Okay, so what happened due to that? Before this, what happened? If you want to taste, what you have to do?
Give different input.
You have to give different input to these two inputs only. Okay, and different combinations are there. And you set a particular value over here. What you have to do?
Check the.
You have to provide a different combination, and that will be loaded over here. From here you have to get the input over here, and then after you can set the value over here. So it's a iterative process, and in that iteration, too many times is there. So to get controllability, what we have done? We have just inserted this scale chain. So directly you can set value over here. Directly you can set value over here or here. You can set over here. You can set the value directly. No need to change the iteration. Okay. So for that, let's say this way we are setting some test factors. So how your chain will work? We'll see that. Okay. See. First, when your test code is in functional mode, it's work as it is function. Okay. Then when you provide test mode is equal to 1, okay, and your ASIC will be 1. So this test factor will be provided from one line only, and it will be shifted one by one. See. Okay. So this way you will get the value directly over here. See. We are getting the value directly over here. 1, 0, 1. And then after, what happens? Again we are making ASIC is equal to 0. Why? Because now we are interested in capturing the value. Capturing the value from where? From here, here and from here. Okay, what is the output of that gate? So for that, we are making ASIC is equal to 0 and we are providing one clock pulse. So your intermediate output will be over there. And then after, we'll just get it at the output side. Where? Over here at the axle. Okay, so to get it, what we have to do? Again, we have to change it to scan mode. We have to change it to scan mode. So ASIC will be 1 and you have to provide clock pulse. So you will get your test response. Okay, so this way it will work. Here, first, second, and third response. So this way you will get your response. So this is only the scan chain operation. And how it will helpful in a testing, I will show you. Let's say you are having SA1. SA1, that means what? Stuck at 1 problem over here. Okay, that means always you will get 1 over here. Whether you provide 0, 0, 0, 1, 1, 0 or 1, 1, always you are having what? 1 over here. So that's a stuck at 1. Okay, so how you are dealing with that? See, first we are providing that particular stimulus. Okay, without this stimulus, if you check, you require too many iterations to set the value over there. ત્યાં આપણે ચેક કરવું હોય કે stuck at 1 છે કે નહીં, તો કઈ રીતે ચેક કરશે? How you can check that stuck at 1 fault is there or not? અહીંયા stuck at 1 fault છે કે નહીં એ આપણે ચેક કરવું હોય તો કઈ રીતે? How we can able to check it? Somehow you have to set the value 0, 0, 0, 1 or 1, 0. Out of that 4 values, the 3 values, first 3 values. So your AND gate output will be what? 0. 0. But if it is stuck at 1, you will get what? 1. 1. So to set that value, you require what? A different iteration. So to remove that iterations, we are inserting this. Okay. So by adding this test stimulus, what you will do? You can set that value. See, 101 we have already added. Okay. So one input of your AND gate will be what? 0 now. One input of your AND gate will be 0 now. Okay. So one input of AND gate will be 0. So your output will be 0. So in last clock, from here, first clock, what you will get? 0. What you will get? 0 at the capture time. But at the capture time, what happens? See, you will get 1. You will get 1 over here due to this circuit. Okay. Actual response will be what?
1, 0,
0, 1, 0, 0, 1. This one is for this. So see 0, 0, 1. But rather than that, you are getting what? 1, 0, 1. You are getting what?
1, 0, 1.
0, 1. Okay. And based on that, you can able to check that stuck at 1 fault is that. Stuck at 1 fault is expected output is what?
1, 0, 0,
0, 0, 1. But you are getting what? 1, 0, 1. So that is faulty output. Okay. And always in DFT, we are not thinking in finding out the position of fault. We are interested in just getting whether circuit is working properly or not. Finding is another. Finding is another. Because this is a small circuit, you can able to tell. But for the bigger circuit, you can't able to find out for this faulty fault. Okay, output, faulty output. Okay, so we are not dealing with the position of that fault, but we are dealing with what? Whether your circuit is faulty or not. Okay, then so this is all about scaling system. Okay, we can say just introduction. For more details, you can read books. Okay, then after MLIST, why MLIST is required? So scenario 1, you can say your SOC. Your SOC will have too many things, right? You will have processor, memory, RAM, ROM, each and everything. But initially, as I told you, your logic part will be 50%. Okay, and the memory part will be 10 to 20%. Okay. In later development, maximum size of your SoC will be consumed by memory. Okay, and then after your reuse logic and new logic, some kind of things. So maximum part of your SoC will be covered by what? Memory logic. So that's why we require what? Memory testing. Otherwise, your device will not work. Scenario 2. This is nothing but you can say just brief about memory. Okay. Initially, in 1956, if you want 5 MB of memory, so it is something like this. You have to load it in your truck, and then you have to transport it. Okay, and it's cost around $3,200. Okay, and nowadays TB of memory you can carry in your pocket. You can carry in your pocket. So that means size of memory is reduced. So it may possible that as well as possible. So it may possible that in your memories due to cell ASIC, whatever fault may possible, or defect may possible. Clear? So for that we require what? MBIT. Okay. So it is kind of a structure. We are adding extra controller with that, and that controller is used to provide what? Address, data, and collect the response and compare. Collect the response and compare it. So that kind of technology is nothing but what? MBIT. Okay. So this is just a overview. Because if I cover in detail, it requires one whole session. Because too many things are there. Memory wrapper is there, then after tap controller is there. From controller you are giving some inputs, you are getting outputs, you are comparing it. Go signal is there, null signal is there. Too many things are there. So it requires another lecture. Okay. But over here I am just giving you overview. Okay. Because recently I am doing this amplitude. Okay. So it's having a structure again. Then if we talk about ADPG, so that is ADPG is nothing but text pattern generations, and then after as well as we are generating response for it. Both the things. Something like this, input as well as output. We are generating both the things, and using comparator, which is inside your ATE, we are comparing and finding whether your IC is working or not. Okay. So in that two different methods are there. Okay. One is random text pattern generation and another one is deterministic. That means two specific faults. When you talk about any IC, what happens? Over there too many nodes are there. હમણાં જે આપણે એક સર્કિટ જોઈ એમાં M node પર SA1 M node and M node you are having what? SA1. એને આપણે કહીએ we call it fault site. We will call it fault site. So too many fault sites are there. So first randomly it will generate pattern, and the number of fault sites it can able to cover, that will be there. And then after deterministic, that means remaining fault sites will be covered. And based on that, different patterns are generated. To test this processor, we require 10,000 patterns. We require 10,000 patterns that will be provided, and it will test in only nanoseconds, few nanoseconds. Okay. So it is something like this. We are providing input, defect-free output, and if defect is there and defective output is there, and we are comparing using comparator. Okay, and we'll check whether it's giving output proper or not. This is actual flow of ATPG. Actual flow of ATPG. This much things we are doing in generating your test patterns. But I am just covering in the short. Okay. Whatever your netlist is there, we'll provide it, and then after we'll create a model, we'll create a steel file that will be used. We'll check DRC. DRC is nothing but design rule check, whether it is following the design or not. Okay. Then after we'll find out the pattern and we are generating a response. So that is our goal method. And this flow is for Tetramax, one of the software that is used for ATP. That is given by Synopsys. Tetramax, Tmax. It's called Tmax. Okay. So yeah, these are nothing but different tools that will be used. Okay. Mostly we are using over there eInforchips, Synopsys tools, and your 930. Okay. So spyglass is actually used for testing your design. That in your design, how many loopholes are there? Okay. So based on this spyglass, when you provide your RTL design to spyglass, it will give you that over this points you are having loopholes. Okay, so you can correct it. Then after for scale insertion, you can use design compiler. It is called DC. Okay, cassette scale you can use, or RC compiler. So different vendors are there and they are providing. So based on our client only provides us this software because it's a costly license. Okay. In which company, as I told you, GUC, I am working, they provide me one mini PC. And that mini PC, a small size of PC is there, that will work in only company premises. You can't operate over here. And that is connected to that Japan client. Okay. In Taiwan, this GUC is located. So servers are there. That is connected with that, and we can work on it. Okay. So for working, they are using what? Obviously for security purpose, they are using Linux. And all the codings, whatever perform, we are just doing in Linux. Okay. And always we are using for editing in Linux. Which kind of editors are there? Editors, simple. They will have notepad. They will have notepad. Similarly, in Linux, they will have editor. Too many editors are there. Gedit, if you know, Gedit, then VI, then Vim. These are the different editors. Okay, I will give you the list of courses also that you can go through. Okay, for your future reference. Okay, so it will be helpful in your career. Okay, further. Then after this prime time, this STA is nothing but what? Static time analysis. Static time analysis for timing match. We are doing prime time. Okay. Then after for ATPG, as I told you, Tetramax. Okay. Fast scale is there. Okay. And counter test is there. For simulation, VCS, NC sim. Okay. And model sim will be used. Okay. So different vendors are there. Okay. This one is for you. Okay. If you want to make a career in this industry, in semiconductor industries, you need this type of course will be completed. Okay, because each and everything over here written will be helpful in your startup. Okay, Linux basically you require. Okay, because all the work will be there inside a Linux only. Okay, scripting you require, so either you can go for shell script or you can go for Perl script, or nowadays they are using Python also. So you can use Python also. Then after Vim editor, as I told you, so that is for your work purpose. Okay, if you want to do a smart work, okay, over there for your design will be, let's say, thousands of lines, so you can't find by scrolling your mouse. Okay, so what you have to do, you have to use some shortcuts, and that shortcuts are available in this Vim. Okay, and this Vim master class, it's a one course on Udemy, as well as it is available on Coursera. So if you go through that course, it's freely available. You can find out which kind of shortcuts you can use to find out the things. Okay, so for that I have mentioned. Then after, this NPTEL course are also freely available. Okay, and that is related to testing. That is related to testing as well as VLSI design. Okay, so you can go through. Yeah. What industry people require or looking, that you have to think. Okay, this is for you only. You can read it. Okay. બેક સાઈડ બ્લેક માર્ક પણ છે, તમે ચેક કરી ઇટ્સ અ ઇંક ઓનલી, વી આર યુઝિંગ ઇંક ફોર બ્લેક માર્ક. ઓકે, thank you very much for your patient listening. Okay, and you can ask if you have any question.
Sir,
I can bring a whole wafer also, but it's too much to carry. It's a whole photo frame, so that's why I have not carried it. Okay, as well as in our company we are having that mounting unit on which we are mounting that particular wafer. That is
सर वो जो आपने बताया सर्कुलर डिस्क होती है, सर्कुलर की होती है आपने
वो आपको फाइंड करना, you have to find. That is related to processing. For processing. आपने क्वेश्चन नहीं पूछा इसलिए मैंने नहीं बताया, कोई पूछता तो मैं बता देता.
तरह भी पूछा था.
फाइंड करो, नहीं तो मैं बताऊंगा. I'll let you know. Okay. कोई तो टेक अवे होना चाहिए आपको यहाँ से. Anyone else? Any questions? Okay.